Science fiction notation. No. Scientific notation. Okay, scientific notation is numbers that represent very large or very small quantities. Very, very, very large or very, very small quantities. That's what we use scientific notation for. Now the definition for scientific notation then is it is a number written as a product. And remember what product is. Product is the answer to a multiplication problem. The product of a number and an integer power of 10. So I'm going to put two examples on now. I'm just going to put an algebraic example so we can define what those things are, and I'm going to put a real world example so you see what this looks like. So the algebraic example would be a, which is our generic number, then it's the product, it's a times 10 to the x. Now, this is our times symbol and this is the variable here. And then in a likewise thing would look like this, 3 times 10 to the 8th. 3 times 10 to the 8th. Now, there's some rules here, okay? First is, we're always going to do a power of 10. This exponent always has to be an integer, which means a positive or negative whole number. I don't know if I want to say whole number, which means it's a whole number or its opposite. That's what an integer is. And this number has rules. So for scientific notation to work, this number has to be between a set parameter. And that means it needs to be greater than or equal to 1 or less than 10. Now the point is, what we want something in this spot here is just to be at the ones place. And then we can manipulate it from there. If we have it at the ones place, then it's uniform throughout all scientific notation, that this will always be the same thing. That's part of the rules for making this work. We can't just all go do anything we want to do. So this number needs to stay between, needs to be 1 or greater and less than 10. And we see that here, 3 times 10 to the 8th. Now that's scientific notation. If we were to write that in standard form, we would write 3, and then that's 3 times 10 to the 8th. Now that's a pretty big number. And we're just manipulating the decimals here. So what we need is we need to move that decimal 8 places. So that's 1, 2, 3, 4, 5, 6, 7, 8. Now I put my comma in too soon. Once I put my 8 in there, I know there's my decimal place. And now I'm just going to count back here. 1, 2, 3, 1, 2, 3. And it's 300 million. So 3 times 10 to the 8th is 300 million. Let's look at a couple of examples now. We're going to take our scientific notation and just move it to standard form. So it's just a basic simple procedure. When we're dealing with a positive exponent, do you think that number is going to be large or small? Good. It's going to be large, so we know that number is going to get bigger than what we see here in our first part here. Here we have a negative exponent, so do you think that's going to be large or small? It's going to be small, right? Because negative exponents, if you remember, are the reciprocal of positive exponents. So if we look at this, all we're going to do is take our number, write our base number here, and then we're going to move it this many places to make it bigger. So if we're going to make it bigger, would we want to add places this way or this way? If we're going to make it bigger, we want to go this way. So we're going to go 1, 2, 3, 4. Now I did that very deliberately, and the reason I did it with the same type of spaces there is then what I'm going to do is go back and I'm going to fill in these zeros so that when I rewrite my number 43400, Now here's my decimal place, so I'm going to go 1, 2, 3, so I can add my comma so I know what exactly that is. So the standard form of this is 43,400. Now let's look at the second one here. So I've got 3.28, so I'm going to write my base number, 3.28. Now I'm looking at my exponent, 10 to the negative third. So now I'm going to move it 3 places, but this time I'm going to move it to the left to make the number smaller. So I'm going to go 1, 2, 3. And right now I'm going to put that decimal right there, just so that I remember. So then I need to add a 0 here and add a 0 here. Then when I rewrite this, I've got 0.00328. And that's my standard representation for that scientific notation. That is, let's see, tenths, hundredths, thousandths, 10,000ths, hundredths, hundred thousandths. So that's 328 hundred thousandths. Now let's go from standard form to scientific notation. So this is probably something that people used more when we had less ability to use calculators. So when we look at this, it was much easier to work with large and small numbers this way. When we look at this, now we've got to get to the rules. The rules matter here. If we remember what the rules are, we have 1 and A and 10. Our number here has to be 1 or greater and less than 10. So let's move the decimal so that the number is 1 or greater and less than 10. So I'm going to go 1, 2, 3, 4. So I've got 3.12 times, now, it's going to be 10 times 10. And the way I remember is, are we representing a small or a large number? Is this a small number or a large? This is a small number. So it's going to be 10 to the negative 1, 2, 3, 4. 10 to the negative fourth. Okay, let's do the other one. Remember our rule. A has to land between, not between, but 1 or greater and less than 10. So let's move our decimal first. So here's our decimal. 1, 2, 3, 4, 5, 6. That gives me 4.525. Does that work? That makes that statement true. It's greater than or equal to 1, less than 10, times 10 to the what? Are we representing a big number or a small number? This is a big number, so we're going to use a positive exponent. It is 1, 2, 3, 4, 5, 6. 10 to the sixth. One last check. Let's look at these two things as a comparison to each other, just so we get some comprehension of how scientific notation can work for us. I have two numbers here. I have 7.21 times 10 to the fifth. I have 1.3 times 10 to the sixth. And my question for you is, which one of these is larger? Which one is a greater value? Now, initially, what you might look at first is, what about this number here? You say, Mr. Romanovich, I can tell right now that this side is greater because 7 is greater than 1. But there's a problem with that too. We don't want to look there first. What we want to look at first is that exponent. Whichever one has the larger exponent, whichever one has the greater exponent, is going to be the greater value. So if we look at this, this is 1.3 times 10 to the sixth, 7.21 times 10 to the fifth, which means that this number is greater than this number by at least a power of 10. So if we look at this, we've got 1.3, 1, 2, 3, 4, 5, 6, 0, 0, 0, 0, 0. That is a comma there and a comma there. 1,300,000. And here I've got 7.21. 1, 2, 3, 4, 5, 0, 0, 0, 721,000. Now that's not close, is it? We've got over 1 million here and 700,000 approximately there. So you can tell when we're checking to see sizes, check first to see which of those exponents is greater. Okay, last thing, let's look at rules for scientific notation. Don't forget that that number that we represent here, that number that we represent, 10, must be greater than or equal to 1 and less than 10. So that's our base number, that's at the beginning. When we write these values, our exponents have to be integers. Negative exponent, small number. Positive exponent, ginormous number.